Everyone knows Copernicus put the sun at the center. What they don't tell you is how he actually figured it out, why he waited 30 years to publish, or the mathematical trick he used that made astronomers go silent. This isn't about a simple idea. This is about a man who rebuilt the cosmos using circles nobody wanted, eliminated a device everybody trusted, and died holding a book that would shatter 1,500 years of certainty. How did a Polish church official working in a cold fortress rewrite reality? What did he see that 14 centuries of experts had missed? Why did his own allies hide what he really believed? Nicholas Copernicus was born February 19th, 1473 in Toruń, a merchant city on the Vistula River in Royal Prussia under the Polish crown. German-speaking family, copper merchant father, 4 children. The youngest boy got the Latin name that would echo through centuries. Father died in the mid-1480s. Uncle Lucas Watson-Rode, a bishop, took him in. That move changed everything. 1491. Copernicus enrolled at the University of Krakow, mathematics, astronomy. He studied the Almagest, Ptolemy's 2nd century masterwork that placed Earth dead center, with planets spinning on circles within circles. He learned about epicycles, those small circles whose centers moved along larger circles called deferents. He learned about the equant, Ptolemy's controversial point from which planets appeared to move at constant angular speed. The equant violated the ancient principle, uniform circular motion. It bothered people. It would obsess Copernicus. 1496, he left Krakow without a degree and headed to Italy. Bologna, canon law. But he lived in the house of Domenico Maria Novara da Ferrara, the astronomy professor. He assisted with observations. He watched the stars. 1500. He went to Rome, lectured on astronomy to crowds of students and scholars. 1501, back to Frombork in Royal Prussia, permission to study medicine in Padua. 1503, doctorate in canon law from Ferrara, not medicine, canon law, then home. 1503 to 1510. He served as secretary and physician to his uncle, the bishop, at Lidzbark Castle. Church politics, administrative duties, economic management. But at night, in whatever time carved out between meetings and medical consultations, Copernicus started calculations. The Ptolemaic system had grown into a monster. Piles of circles. Observations from 15 centuries hadn't matched predictions. Calendar reform was desperate business because the dates for Easter kept drifting. The tropical year length was wrong. Something fundamental was broken. 1508, maybe 1510. Copernicus had his revelation, not from new observations. From reading Ptolemy more carefully than anyone else, he saw patterns. The inferior planets, Mercury and Venus, never strayed far from the Sun. Mercury maxed out at 22 degrees. Venus at 48 degrees. In the Ptolemaic model, this required complex constraints, epicycles locked in step with the Sun's position. For the superior planets, Mars, Jupiter, Saturn, the retrograde motion, that backward loop they traced in the sky, always happened when they stood opposite the Sun as viewed from Earth. Retrograde required the 3 superior planets to move around their epicycles in lockstep with one another and with the Sun's annual motion. Every planetary model in Ptolemy's system had the Sun's period embedded in it. Why? Copernicus realized if Earth moved around the Sun, all those constraints collapsed into one elegant explanation. Retrograde motion wasn't real planetary motion. It was parallax. The appearance of backward motion came from Earth overtaking the outer planets, or the inner planets overtaking Earth. Mercury and Venus stayed close to the Sun because they orbited inside Earth's orbit. The lockstep problem vanished. One motion, Earth's annual revolution, explained the solar connection in every single planet. Between 1510 and 1514, he wrote a short manuscript, 40 pages, Latin, no title. He called it nothing. Later generations called it the Commentariolus, the little commentary. He made a few handwritten copies and gave them to close friends. A library catalog from May 1st, 1514 listed a manuscript of 6 leaves expounding a theory where Earth moves and the Sun stands still. No author name. That's how it circulated. Anonymous, radical, quiet. The Commentariolus laid out 7 axioms. 1. There's no single center for all celestial circles. 2. The center of the Earth is not the center of the universe, only the center of the lunar sphere. 3. All spheres revolve around the Sun, which is near the center of the universe. 4. The distance from Earth to the Sun is tiny compared to the distance to the fixed stars. 5. The apparent daily motion of the heavens comes from Earth's rotation on its axis. 6. The apparent annual motion of the Sun comes from Earth's revolution around the Sun. 7. The apparent retrograde motion of the planets arises from Earth's motion. He He claimed he could explain all celestial motions with just 34 circles. Ptolemy's updated system, refined by Georg von Feuerbach and Johannes Regiomontanus in the 1500s, used about 40 circles. Some counts put Ptolemy's original at 80 dies, but that was inflated. Copernicus promised simplicity. 34 circles, uniform motion, no equant. That last part mattered. The equant was Ptolemy's cheat. To make planets match observations, Ptolemy put them on circles moving at uniform speed around a point offset from the deference center. Technically violated the principle of uniform circular motion around the circle's own center. Philosophers hated it. Astronomers used it because it worked. Copernicus rejected it on philosophical grounds. He replaced the equant with additional small epicycles to produce the same mathematical effect. More circles, but pure circles, philosophically clean. Here's what nobody tells you. Copernicus didn't invent the math. Islamic astronomers in the 13th and 14th centuries, working in Moraga and Damascus, had already developed the techniques. Nasir al-Din al-Tusi created the Tusi couple, a mechanism using two epicycles to generate linear motion. Muwayyad al-Din al-Urdi developed the Urdi lemma. Ibn al-Shatir, working in Damascus in the 1400s, built models for the moon and Mercury nearly identical to what Copernicus would use. Al-Shatir eliminated Ptolemy's equant using extra epicycles, the exact same method Copernicus used in the Commentariolus. Historians have fought for decades over whether Copernicus saw Arabic manuscripts. No Latin translations existed, no smoking gun, but the mathematics matched too closely. Most scholars now think either Copernicus had access through Byzantine intermediaries, or, less likely, he independently reinvented the same techniques, solving the same problems with the same tools. Either way, Copernicus was not working in a vacuum. He spent the next 30 years refining the full model, making observations, calculating. Frombork, his home from 1510 onward, sat on the Baltic coast, terrible location for astronomy. Cold, cloudy, but he observed when he could. He used observations from Bernhard Walther, a student of Regiomontanus, 45 Mercury observations. He borrowed from Islamic astronomers, al-Battani, Thabit ibn Qurra, al-Zarqali. Averroes, al-Bitruji. He cited them in his final work. By the 1530s, his book was substantially complete, manuscript in his own hand, later found in the Jagiellonian Library in Krakow, catalog number BJ 10,000. He kept revising. Different types of paper used in different sections show the composition timeline. He hesitated to publish, feared ridicule. 1533, Johann Albrecht Widmanstätter delivered lectures in Rome outlining Copernicus's theory. Pope Clement VII and several cardinals heard them. They showed interest. November 1st, 1536, Cardinal Nicholas von Schönberg wrote Copernicus from Rome asking for a copy of his writings at the earliest possible moment. Encouragement from the top. Still, Copernicus delayed. If you value documented astronomical history and mathematical innovation like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from De Revolutionibus Orbium Coelestium 1st edition, Nuremberg 1543 Dars, held at the Jagiellonian Library Krakow, and from Noel Swerdlow and Otto Neugebauer's Mathematical Astronomy in Copernicus's De Revolutionibus, at University of Chicago Press, 1984, which provides the most detailed technical analysis of Copernicus's planetary models and their Islamic precedents. Published in the Journal for the History of Astronomy and cited in Bernard Goldstein's work on the origin of Copernicus's heliocentric system in the British Journal for the History of Science, 1985. Now back to the information. 1539, a young mathematician showed up at Frombork, Georg Joachim Rheticus, 25 years old, Protestant from Wittenberg, came to study with a 70-year-old Catholic canon. Dangerous time for Protestants and Catholics to collaborate, but astronomy crossed those lines. Rheticus read the manuscript, immediately grasped its importance. He wrote a summary, a non-technical open letter addressed to his former teacher, Johannes Schoner. He published it in Danzig in 1540 as Narratio Prima, the first account. 32 pages describing Copernicus's system without the heavy mathematics. It got attention. Second edition in Basel 1541, positive reception. Under pressure from Rheticus and seeing the Narratio Prima didn't cause outrage, Copernicus finally agreed. June 9th, 1541, Rheticus wrote that Copernicus had given consent for publication. August 29th, 1541, the manuscript was ready. Rheticus took it to Wittenberg, gave it to printer Johannes Petreius in Nuremberg. Then Rheticus left Nuremberg for a professorship in Leipzig. Petreius couldn't supervise the printing. He asked Andreas Osiander, a Lutheran theologian in Nuremberg, to oversee it. Osiander made an unauthorized move. He removed Copernicus's original preface and wrote his own anonymous letter to the reader. Printed unsigned before Copernicus's dedication to Pope Paul III, Osiander's letter claimed Copernicus's heliocentric system was just a mathematical hypothesis for easier calculations, not a claim about physical reality. It is the duty of an astronomer to compose the history of celestial motions through careful study. Then he must conceive and devise the causes of these motions or hypotheses about them, since he cannot in any way attain to the true causes. He will adopt whatever suppositions enable the motions to be computed correctly according to geometrical principles. Readers assumed Copernicus wrote it. He didn't. He never saw it. The book arrived at his deathbed, May 24th, 1543. Copernicus died in Fromborg. Cerebral hemorrhage. Legend says a printed copy of De Revolutionibus was placed in his hands on his deathbed. Probably true. He allegedly regained consciousness long enough to see it. Then gone. 70 years old. De Revolutionibus Orbium Coelestium. 6 books, 400 pages. First edition, Nuremberg 1543. Second edition, Basel 1566. Initial print run, 400 copies. It didn't sell out. Copernicus had made it intensely technical, impenetrable to anyone but professional astronomers. That saved it from immediate controversy. Book structure followed Ptolemy's Almagest closely. Book 1, General Vision of Heliocentrism. 11 chapters. The cosmos is spherical. The Earth is spherical. Land and water make one globe. The heavens move uniformly in circles or combinations of circles. Earth has 3 motions: daily rotation on its axis, annual revolution around the sun, and annual tilting of its axis to maintain the same orientation relative to the stars. Book 2, Spherical Astronomy and Star Catalog. Book 3, Precession of the Equinoxes and Solar Theory. Book 4, Lunar Motions and Eclipses. Book 5, Planetary Longitude. Book 6, Planetary Latitude. The planetary longitude calculations in Book 5 were Copernicus's most demanding accomplishment. 20 years of observations, tedious calculations. Contemporaries recognized it as equal to Ptolemy's achievement. Owen Gingerich, the Harvard astronomer who spent 35 years tracking down every surviving first and second edition copy, found nearly all the leading mathematicians and astronomers of the time owned and read De Revolutionibus. But his marginalia analysis showed they skipped the cosmology and mined the technical planetary calculations. They treated it as a computational toolkit, not a cosmological revolution. The book gave precise numbers: planetary orbital radii and astronomical units, where Earth's orbit radius equaled 1, Saturn 9.175, Jupiter 5.219, Mars 1.524, Venus 0.7193, Mercury 0.3771. The Moon stayed in Earth orbit. Those distances made sense only in a heliocentric system. In Ptolemy's geocentric model, you couldn't determine absolute distances, only angular positions. Copernicus had unlocked the scale of the solar system. That was genius, not just saying Earth moves, giving the actual architecture. Copernicus's system still used epicycles, lots of them. He needed them to maintain uniform circular motion while matching observations. Final count, 48 circles for all planets. Ptolemy's refined system, 40 circles. Copernicus added 8 more. The claim of simplicity was oversold, but conceptual simplicity was real. Retrograde motion explained by geometry, not mysterious epicycles all tied to the sun. The sun's role in every planetary model explained by one central fact: Earth orbited the sun. That was elegant. That was revolutionary, even if the math was messy. Accuracy? About the same as Ptolemy's updated tables. Copernicus's predictions were good for his time, but not dramatically better. His model couldn't predict planetary positions to better than about 8 minutes of arc. That was the tolerance. For most astronomers, that was enough to stay neutral. Use Copernican calculations without accepting heliocentrism. Erasmus Reinhold, professor at Wittenberg, published the Prutnik tables in 1551 based on Copernicus's models. Widely used, Reinhold never publicly endorsed Earth's motion. Thomas Blundeville in 1594 summarized the attitude. Copernicus affirmeth that the earth turneth about, and that the sun standeth still in the midst of the heavens, by help of which false supposition he hath made truer demonstrations of the motions and revolutions of the celestial spheres than ever were made before. The Catholic Church initially ignored the book. Osiander's anonymous preface helped. It framed heliocentrism as a calculating device. not physical truth. But Copernicus's own preface, his dedication to Pope Paul III, made clear he believed in a moving Earth. He wrote, "I debated with myself for a long time whether to publish the volume which I wrote to prove the Earth's motion, or rather to follow the example of the Pythagoreans, who used to transmit philosophy's secrets only to kinsmen and friends, not in writing, but by word of mouth." He described why he chose heliocentrism. Astronomers do not agree among themselves in their investigations. They are so uncertain about the motion of the sun and moon that they cannot establish and observe a constant length even for the tropical year. He argued the Ptolemaic system was incoherent, a patchwork, pieces that didn't fit. He compared it to a monster. With them, it is as though an artist were to gather hands, feet, head, and other members from diverse models, each part excellently drawn, but not related to a single body, and since they in no way match each other, the result would be monster rather than man. Opposition came slowly. Martin Luther heard rumors in 1539 discert before publication. In his table talks, he said, "People gave ear to an upstart astrologer who strove to show that the earth revolves, not the heavens or the firmament, the sun and the moon. This fool wishes to reverse the entire science of astronomy. But sacred scripture tells us that Joshua commanded the sun to stand still and not the earth." When De Revolutionibus finally appeared, Luther's concern didn't spread immediately. The book was too technical. It circulated among specialists. The real problem was physical. Aristotelian physics dominated. Heavy objects fell to Earth's center because Earth was the universe's center. Why would they fall in a sun-centered system? Copernicus had no answer. His contemporary Tycho Brahe, the greatest observational astronomer of the age, built his own cosmology. The Tychonic system, Earth stationary at the center, moon and sun orbit Earth. All other planets orbit the moving sun, mathematically equivalent to Copernicus's model. Brahe collected unprecedented data from his observatory Uraniborg on the Danish island of Hyven, massive instruments, no telescope yet invented, naked eye precision to about 2 minutes of arc. Brahe rejected Copernicus on physical grounds. He said, "The Copernican system expertly and completely circumvents all that is superfluous or discordant in the system of Ptolemy. On no point does it offend the principle of mathematics. Yet it ascribes to the Earth that hulking, lazy body, unfit for motion. A motion as quick as that of the ethereal torches, and a triple motion at that." 45 years after publication, De Revolutionibus had a small but growing following. Not a revolution yet, a technical alternative. Then came the second generation, Johannes Kepler, Tycho's assistant. Inherited Tycho's data when Tycho died in 1601. Kepler was a convinced Copernican, but he couldn't make Mars fit a circular orbit using Tycho's observations. 8 minutes of arc error. Small, but Kepler trusted Tycho's precision. He spent years recalculating, trying different models. Finally, against his will, he abandoned perfect circles. 1609, Astronomia Nova, new astronomy. The orbit of Mars is an ellipse with the sun at one focus. First law, planets sweep out equal areas in equal times. Second law, the equant fell. The epicycles fell. Ellipses explained everything, but it took Kepler's genius and Tycho's data to get there. Copernicus died, never knowing ellipses would vindicate his heliocentric intuition and obliterate his circular epicycles. Galileo Galilei came next. 1610, telescope. Saw Jupiter's moons orbiting Jupiter, not Earth. Proof that not everything orbited Earth. Saw Venus showed phases like the moon, which only made sense if Venus orbited the sun. Published in 1613. Letters on sunspots. Public support for Copernicanism. Attacked Aristotelian physics. That got the church's attention. 1616. De Revolutionibus placed on the index of prohibited books. 73 years after publication. Not banned outright. Suspended until corrected. 9 sentences had to be removed or changed. Sentences asserting heliocentrism as certain truth rather than hypothesis. Corrections approved in 1620, book allowed with edits for qualified scholars, but it was never reprinted with changes, remained on the index until 1758. Pope Benedict XIV removed it from his revised index, 215 years after Copernicus's death. By then, Isaac Newton had settled the matter. 1687, Philosophiae Naturalis, Principia Mathematica, Universal Gravitation, Laws of Motion, mathematical proof that elliptical orbits followed from an inverse square force centered on the sun. Suddenly, everything clicked. Why Earth moved, why planets orbited in ellipses, why moons orbited planets, why objects fell. one set of laws for heaven and earth. No special physics for the heavens. The Copernican revolution became complete only after Kepler provided the correct orbits and Newton provided the physics. But here's what makes Copernicus remarkable. He started it with ancient tools. No telescope, no new observations of consequence, no new physics, just Ptolemy's data, Islamic mathematics, and the courage to ask, what if the patterns in the Ptolemaic system aren't coincidences? What if the sun's role in every planetary model means the sun is the center? He saw through 1,500 years of certainty by reading to Ptolemy better than anyone. He eliminated the equant not because he had proof, but because it offended his sense of mathematical purity. He spent 30 years calculating to show heliocentrism worked mathematically, even if he couldn't explain why physically. He feared ridicule so much he waited until death's door to publish. Osiander's sabotage of his preface meant most readers thought Copernicus himself claimed heliocentrism was just a calculating trick. Copernicus never got to defend his belief that Earth truly moved. Let's go deeper into what he actually calculated. Book 5 of De Revolutionibus gives the planetary longitude models. Each planet required multiple parameters: orbital period, orbital radius, eccentricity, epicycle radius, rate of rotation on the epicycle. For Saturn, period 29.457 years. Deferent radius, 9.175 in astronomical units. Eccentricity, 0.07. Epicycle radius to account for remaining irregularities. For Jupiter, period 11.862 years. Deferent radius, 5.219. Eccentricity, 0.048. For Mars, period 1.881 years. Deferent radius, 1.524. Eccentricity, 0.093. Mars was hardest because of its large eccentricity. Kepler would struggle with it for the same reason. For Venus, period 0.723 years, about 9 months. Deferent radius, 0.7193. Eccentricity, 0.007. Small eccentricity, nearly circular. For Mercury, period 0.241 years, about 3 months. Deferent radius, 0.3771. Eccentricity, 0.206. Highest eccentricity. Mercury's model was the most complex, requiring the Tusi couple-like mechanism to handle its extreme variations. Earth's orbit wasn't perfectly centered on the sun. Copernicus placed the sun slightly off-center by about 3% of Earth's orbital radius. This offset explained the varying length of the seasons. Spring and summer are longer than fall and winter in the northern hemisphere because Earth moves slower when farther from the sun. Copernicus captured this with geometric offsets, not with Kepler's later insight about elliptical orbits and varying speeds. Earth's 3 motions. First, daily rotation on its axis. 1 complete turn every 24 hours. Explains day and night. Explains the apparent daily motion of stars, sun, moon, planets. Second, annual revolution around the sun. 1 complete orbit every 365 days, 5 hours, 49 minutes. Explains the seasons because Earth's axis is tilted 23.5 degrees to the orbital plane. When the northern hemisphere tilts toward the sun, summer. 6 months later, tilted away, winter. Third motion, the annual shift in the tilt direction. Actually, a slow wobble called precession. Earth's axis traces a circle over 26,000 years. Copernicus approximated this with a yearly small motion to keep Earth's axis pointing the same direction relative to the stars as it orbited. He knew it was more complex, but simplified for his model. The fixed stars. Copernicus placed them vastly farther away than anyone before. He had to. If Earth moved around the sun, stars should show parallax, an apparent shift in position when viewed from opposite sides of Earth's orbit. No parallax observed. Copernicus solved this by making the stars so far away that parallax was too small to detect. He estimated the star sphere was at least 700 times farther than Saturn. That made the universe immensely larger than the medieval cosmos. Most people couldn't accept that. Empty space terrified them, but Copernicus was right. First stellar parallax wasn't measured until 1838 by Friedrich Bessel. Stars are millions of times farther than Saturn. Copernicus cited ancient precedent, Aristarchus of Samos, 3rd century BCE, Greek astronomer. First known heliocentric model, Aristarchus calculated the sun was 18 to 20 times farther than the moon and proposed Earth rotated on its axis and orbited the sun. His work didn't survive, except in fragments quoted by Archimedes. Copernicus mentioned Aristarchus in an early manuscript of De Revolutionibus, stating, Philolaus believed in the mobility of the Earth, and some even say that Aristarchus of Samos was of that opinion. He crossed out this reference before publication. Why? Possibly because Aristarchus was attacked for impiety. Cleanthes, the Stoic, wanted Aristarchus charged with moving the hearth of the universe. Copernicus may have wanted to avoid that parallel, or he realized Aristarchus's model differed in important details. Either way, the published version only referenced Pythagorean philosophers like Philolaos, Heraclides Ponticus, and Ecphantus, who proposed Earth moved but didn't place the sun at the center. Copernicus also credited his reading of Cicero and Plutarch. In Cicero's writings, he found an account of Hyacinthes' theory. Plutarch described Pythagorean ideas about Earth's motion. These ancient hints gave Copernicus historical cover. He wasn't inventing heresy. He was reviving ancient wisdom. That framing helped. But it also obscured his real originality, using heliocentrism to determine actual planetary distances and unlock the solar system's architecture. Now the reception. Poland embraced Copernicus, eventually. Germany saw Rheticus promoted at Wittenberg and Leipzig. England. Thomas Digges published a translation of key parts in 1576, removing the Earth-centric limits on the star sphere and proposing an infinite universe. Digges was the first English Copernican. Italy. Giordano Bruno advocated for heliocentrism and an infinite universe filled with other worlds. 1600. The Inquisition burned him at the stake for multiple heresies, including Copernicanism. Galileo was more cautious, but ultimately faced trial in 1633. Forced to recant. House arrest until death. France, slow adoption. René Descartes developed his own vortex theory of planetary motion. Heliocentric in spirit, if not in technical detail. England again. Isaac Newton at Cambridge. By the 1680s, the leading edge of science had moved past Copernicus, Kepler's ellipses, Galileo's observations, Newton's mathematics. Heliocentrism was no longer controversial in the scientific community. But teaching it remained dangerous in Catholic countries until the mid-1700s. Compare the numbers. Ptolemy's Almagest, 13 books. Copernicus's De Revolutionibus, 6 books. Ptolemy worked in Alexandria around 150 CE, 1400 years of tradition. Copernicus worked in Frombork, isolated, cold, no major observatory, no research team, just one man, his books, a few instruments, and the conviction that the patterns meant something. Ptolemy's system, 40-plus circles in its refined form. Copernicus's system, 48 circles, almost the same complexity. Copernicus's advantage, conceptual unity. Everything linked to Earth's motion and the sun's position. Ptolemy's disadvantage, no unifying principle. Each planet modeled separately. The solar connection unexplained. Accuracy comparison. Ptolemy's tables. Refined over centuries, predicted planetary positions within 10 minutes of arc for most cases. Copernicus's tables, the Prutnik tables published by Reinhold based on Copernicus's models, achieved similar accuracy, around 5 to 10 minutes of arc. Kepler, using Tycho's data, got down to 2 minutes of arc with elliptical orbits. That's when Copernican astronomy finally surpassed Ptolemaic astronomy in predictive power. But prediction wasn't the point for Copernicus. Philosophical consistency was. He wanted a system that didn't violate the principles it claimed to uphold. Ptolemy's Equant did. Copernicus's Epicycles didn't. The manuscript history. Copernicus's autograph manuscript of De Revolutionibus survived. After his death, Rheticus received it. It passed through Heidelberg. Ended up in Prague, rediscovered and studied in the 19th century. Different paper types and different sections allowed scholars to reconstruct composition phases. Early sections had different watermarks than later sections. Copernicus wrote in stages over decades. The Commentariolus circulated in manuscript until Tycho Brahe obtained a copy in 1575. Tycho gave copies to students and colleagues, eventually printed in 1878, first complete public edition, 364 years after it was written. The document that introduced heliocentrism to Europe spent centuries known only to insiders. Copernicus's observational work, limited but significant. He observed the summer solstice carefully to correct the calendar. He tracked Mars, Jupiter, Saturn for their retrograde loops. He measured lunar eclipses with colleagues in Krakow between 1515 and 1530. He recorded solar and lunar positions to refine orbital parameters, but most of his data came from others. Ptolemy's observations from the Almagest, Islamic observations from al-Battani and others, Walther's Mercury observations. Copernicus was primarily a mathematician and theorist, not an observer. His genius was synthesis, seeing how to reorganize existing data into a new framework. The intellectual context matters. 1500s, Europe, Renaissance humanism, rediscovery of ancient texts, critical examination of received authority. Gutenberg's printing press spread knowledge fast. Columbus reached the Americas in 1492. Copernicus was born in a world discovering that ancient geography was wrong. Maybe ancient cosmology was wrong too. The Reformation split Christianity, Luther in 1517. If religious authority could be challenged, scientific authority could be challenged. Copernicus lived through those upheavals. They created space for radical ideas, but also danger, heresy trials, burnings. Copernicus waited until he had nothing to lose. His personal life: canon of Frombork Cathedral from 1510 until death, managed church estates, practiced medicine, advised on currency reform, wrote a treatise on money in 1526, never married, Catholic canon, took his duties seriously, but astronomy was his passion. He built his own observatory, a small tower in Frombork where he could make observations, survived the Polish-Teutonic Wars. Frombork was attacked in 1520 during the war between Poland and the Teutonic Knights. Copernicus organized the defense of Ulstein Castle as administrator. He returned to astronomy when peace came. A man of many roles: astronomer, mathematician, physician, economist, administrator, diplomat. But history remembers one thing: he moved the Earth, the final reveal. In 2008, Dachshund archaeologists in Frombork Cathedral found skeletal remains beneath the floor near the altar. DNA testing and facial reconstruction in 2005 confirmed Nicholas Copernicus buried in the cathedral he served. No monument for 467 years. Just bones in the floor. In 2010, they reburied him with honors. Granite tombstone with a model of the solar system, sun at the center, 6 planets orbiting, a long-delayed recognition, but the tombstone tells the truth. Copernicus didn't just propose heliocentrism. He built the model that let Kepler and Newton finish the revolution. He calculated the planetary distances that revealed the solar system's true scale. He showed that Earth was a planet among planets, not the special center of creation. That intellectual earthquake took a century to fully hit. But it started in a cold fortress on the Baltic with a man who trusted mathematics over appearances and refused to accept the equant. Copernicus died May 24th, 1543, the same year his book appeared, The Ultimate Timing. No public controversy in his lifetime, no trial. No forced recantation. He slipped away before the storm. Whether by luck or design, he avoided what Galileo suffered. But his book did the work, slowly, quietly, across generations. Astronomers mined its calculations. Philosophers debated its implications. The church eventually noticed and reacted. But too late. The idea was out. Earth moves. The sun stands still. The universe is vastly larger than we thought. And we are not the center. Copernicus proved it with circles and numbers, without a telescope, without seeing Jupiter's moons or Venus's phases or stellar parallax. He proved it with pure reason applied to ancient data. That's the genius nobody talks about. Not new observations, not new instruments. Just seeing what everyone else had looked at for 1,500 years and understanding it differently. The courage to say, what if we've been wrong? What if the center is somewhere else? And then spending 30 years making sure the mathematics worked. One more number. 1838, Friedrich Bessel measured the first stellar parallax, 61 Cygni, 0.31 arc seconds. That's how far the star appeared to shift when viewed from opposite sides of Earth's orbit. Tiny. Barely detectable even with the best telescopes of the 1800s. Copernicus predicted stars were so far away that parallax would be undetectable to the naked eye. He was right. 300 years later, instruments caught up to his prediction. The universe he imagined was real. The distances he implied were accurate. He never saw the proof. He died believing it on mathematical faith. That faith, backed by 48 circles and 6 books of calculations, changed everything. Let's rewind. Before the shattered cosmos, before the telescope, before the pyres and the trials, there was a single, driving obsession: purity. Nicholas Copernicus was not a wild-eyed revolutionary trying to overturn the world for the sake of rebellion. He was a conservative, a purist, a man haunted by a ghost in Ptolemy's machine, the equant. To understand why Copernicus sacrificed the stability of the Earth itself, you have to understand why this one mathematical device was an unforgivable sin against the heavens. The ancients, Pythagoras and Plato, had bequeathed to astronomy a sacred duty, to save the appearances, to explain the messy, wandering paths of the planets using only the most perfect form, the circle, and the most perfect motion, uniform speed. The heavens were the realm of the divine, and God was a geometer who would only use the most perfect tools. Ptolemy's system was a masterpiece of this principle, a clockwork of circles turning on other circles, but in one crucial place, he cheated. To make the model for Mars actually predict where the planet would be, he had to make its epicycle move at a constant speed not as seen from the center of its main circle, the deferent tangenters, but from another point, offset from the center. This was the equant. The planet was moving on a perfect circle, but it was not moving with perfect apparatus. Uniform motion around that circle's own center. It was a fudge factor, a mathematical trick that broke the philosophical rule. For 1400 years, astronomers lived with this necessary evil. It worked. It produced the tables. It let them predict eclipses and conjunctions. But it was a stain on the perfection of the cosmos. It was a monster in the cathedral. Copernicus's entire 30-year project was, at its heart, an exorcism. He wanted to kill the equant. Here's the secret that historians now understand. He did not invent the murder weapon. He found it, or reinvented it, from a source few in Latin Europe knew existed: the Islamic world. In the 13th century, at the Maragheh Observatory in what is now Iran, the astronomer Nasir al-Din al-Tusi had wrestled with the same problem. He devised an ingenious mechanism of two nested circles, a small one rolling perfectly inside a larger one twice its diameter. The result? A point on the circumference of the smaller circle traced a perfect straight line. He had generated linear motion from pure circular motion. This was the Tusi couple. 1 century later, in the 1400s, a brilliant astronomer named Ibn al-Shatir, working as a timekeeper at the Great Mosque of Damascus, took these new mathematical tools and rebuilt the entire Ptolemaic system. He created a lunar model and planetary models that completely eliminated the need for the equant. He did it by adding more epicycles, using the Tusi couple and other devices to mimic the effects of the equant with pure, strict, unadulterated circles. His final model for Mercury is mathematically almost identical to the one Copernicus would present in De Revolutionibus 150 years later. There is no direct evidence Copernicus read al-Shatir's work, but the mathematical correspondence is too precise to be a mere coincidence. The solution to the problem that obsessed him, the technique that made his system philosophically superior in his own eyes, came not from a flash of European genius, but from the intellectual lineage of Damascus and Maragheh. He was not the first to slay the monster. He was the one who tied that victory to a sun-centered cosmos. His great work was not just a new cosmology, it was the vehicle that unknowingly transmitted advanced Islamic mathematics into the heart of Renaissance astronomy. When his fellow astronomers first saw his work, this is what made them go silent. Not the moving Earth, that was absurd, physically impossible. It was the elimination of the equant. They saw that he had done it. He had restored the philosophical purity of uniform circular motion. They marveled at the mathematical elegance, even as they rejected the physical premise. This is why they used his book. They mined it for its superior mathematical models for the moon and planets, treating it as a high-level toolbox while ignoring the cosmological framework. The first generation of readers didn't see a revolution. They saw a restoration, a successful attempt to cleanse astronomy of its long-standing philosophical stain, but the cost of that cleansing was catastrophic in ways Copernicus himself could not have fully grasped. His system was not just a rearrangement of the planets. It was a wrecking ball aimed at the very structure of reality. The Aristotelian world was a closed, finite, and deeply meaningful place. Earth was at the bottom, the sump of the universe, made of 4 corruptible elements: earth, water, air, fire. The heavens, starting with the moon, were a different realm entirely, made of a 5th element, the ether, which was perfect, eternal, and unchanging. The planets were not rocks. They were divine lights embedded in solid, nested crystalline spheres that rotated around the Earth, carrying them on their journeys. This cosmic architecture was physics, metaphysics, and theology all in one. It separated the messy, mortal world from the perfect, divine heavens. Copernicus smashed it to pieces. If Earth was just another planet orbiting the Sun, then the distinction between the terrestrial and celestial realms dissolved. The Earth was in the heavens. This meant the heavens were not made of some perfect ether. They were made of the same stuff as Earth. A rock was a rock, whether on Earth or on Mars. This was a terrifying degradation of the heavens. Worse, the system of crystalline spheres no longer made physical sense. How could the sphere of Mars cut through the sphere of the Sun as the Sun carried Mars' orbit around the Earth, as in Tycho's later model? How could Venus and Mercury's spheres pass through the Sun's? The whole physical mechanism that held the universe together for 2,000 years simply evaporated, leaving a void. And into that void rushed an even greater terror: infinity. If the stars were truly so far away that their parallax was undetectable, the space between Saturn and the stars was vast, empty, and useless. God, the ultimate rational creator, did not make things without purpose. Why create so much emptiness? In 1576, the English astronomer Thomas Digges took the next logical step. He translated parts of De Revolutionibus and drew a diagram of the cosmos, but instead of an outer sphere of stars, he depicted the stars scattering outwards into infinity. Our sun was just one star among many. This was the idea that seized the imagination of the philosopher Giordano Bruno. He traveled Europe, preaching not just a heliocentric system, but an infinite universe with infinite worlds, each with its own sun and its own life, perhaps its own saviors. This was not astronomy anymore. It was a head-on collision with Catholic dogma about the uniqueness of Christ's incarnation and humanity's special place in creation. When the Inquisition burned Bruno at the stake in Rome in the year 1600, they burned him for these heresies, born from the shattered container of the old cosmos. The smoke from that fire hung over Galileo's generation, a stark warning of where Copernican ideas could lead. Amidst this turmoil stood the greatest astronomer of the age, a man who saw the genius of Copernicus but could not accept his conclusions. Tycho Brahe. He was no fool clinging to dogma. He was an empiricist, a man who trusted data above all else. His observatory, Uraniborg, was the finest scientific instrument in the world. He measured the positions of the stars and planets with a precision that was 4 times better than anyone before him, and his data told him Copernicus was wrong. First, the parallax problem. Tycho's instruments were exquisite, yet he could not detect any stellar parallax. He calculated that for this to be true in a Copernican system, the stars would have to be at least 7,000 times more distant than the sun, making the void of space incomprehensibly vast. Second, the physics. If the Earth, this hulking, lazy body, spun on its axis at 1,000 miles per hour, why wasn't everything not nailed down flung into space? Why didn't a cannonball fired west travel much farther than one fired east? Aristotle's physics provided a complete and coherent, if wrong, explanation for how things worked on a stationary Earth. Copernicus offered no new physics to explain how things would work on a moving one. Faced with the mathematical elegance of Copernicus on one hand and the overwhelming physical and observational evidence against it on the other, Tycho did what any great scientist would do. He proposed a third way. His Tychonic system was a brilliant compromise. The Earth remained stationary at the center, unmoving, satisfying both scripture and common sense physics. The sun and moon orbited the Earth, and all the other planets, Mercury, Venus, Mars, Jupiter, Saturn, orbited the moving sun. Mathematically, this system is identical to the Copernican system. All the relative motions are the same. It explained the phases of Venus and the bounded elongation of the inner planets perfectly. It accounted for the retrograde loops as a result of the sun's motion, and it did so without moving the Earth. For most working astronomers in the late 16th century, Tycho's model was the superior choice. It had all the mathematical benefits of Copernicus without any of the physical or theological absurdities. The revolution was stalled. The final battle for the cosmos would be fought not in the town square or the Inquisitor's chamber, but in the quiet margins of a 400-page book. In the 20th century, the historian Owen Gingerich embarked on a 30-year quest to track down and personally inspect every surviving copy of the first and second editions of De Revolutionibus, over 600 books in total. He called it his Copernicus census. What he found transformed our understanding of the scientific revolution. These books were not unread curiosities sitting on shelves. They were working documents. Their margins were filled with notes, calculations, corrections, and arguments from the greatest astronomical minds of the 16th and 17th centuries. He could trace the book's passage from one astronomer to another. He saw the heavy annotations of Erasmus Reinhold, who used Copernicus's math to create the widely used Prutnik tables while never publicly endorsing his cosmology. He saw the notes of Michael Maestlin, Kepler's teacher, who taught the Copernican system to his gifted students in private. He saw how astronomers praised the lunar model but crossed out the sections on the Earth's motion. They were arguing with Copernicus, testing him, using his labor. The book was a seed, and these marginal notes were the traces of its slow, difficult germination. It wasn't a sudden explosion, but a gradual, painstaking process of assimilation and verification. The revolution didn't happen in 1543. It happened over the next 150 years, in the minds of the men who filled the margins of De Revolutionibus with their questions, their doubts, and ultimately, their proofs. Copernicus provided the new grammar for the language of the heavens. It took Kepler to write the first true poetry with it, and Newton to reveal the laws that governed it all. The man in the cold fortress on the Baltic began a conversation that he would never live to hear the end of, a dialogue between the book he wrote and the generations of readers who would, page by page, calculation by calculation, dismantle one universe and build another in its place.